our
This
agenda.
conference will now be recorded.
Hi, good morning, good evening, everyone. Thank you for joining today. This is the TAP meeting, the biweekly TAP meeting call. It's our 22nd meeting. And today we have the honor of having good friends of TAP here joining us today. With us today are Pasi Vaananen, who is a system architect at Red Hat, part of the CTO office, and is focused on run edge telco enablement solutions. And presenting is Timo. Timo is Chief Technologies at Red Hat and is working with global telco technology enablement. And they're going to give us today a call about synchronization implementations on Linux and Kubernetes clusters. So thanks for coming today. What we have planned is to have an introduction on the market segments with the different synchronization requirements and covering the demand and in depth. And also we have a wide forum of attendees today, and I'm sure that questions such as scaling and operating Linux synchronization in respective environments is going to be a hot topic and probably a lot of questions, and we do encourage discussion. So for those who join us today, please present your name and your affiliation on the screen, and feel free to plug in your questions. With that, thank you. I'm going to pass it now to Timo and Pasi.
Okay, thanks a lot. So first of all, my name is Timo Jokiaho, based at Red Hat Finland. I've been at Red Hat for 7 years, and before that I tried Nokia, I tried Huawei, I tried Samsung, and then I ended up at the Red Hat, which is excellent. And I'm going to give the introductory part, and Pasi will talk about all the good stuff. Pasi, you want to introduce yourself as well?
All right, my name is Pasi Vaananen, and I have been on the telco industry for past 25 years. Before that, I was doing more complicated networking, but this is good enough for me for now. And I've been on, I'm in Massachusetts in the US. I've been in places like Nokia. I moved to US as Nokia employee for 2 years, and that was like 25 years ago. So, and since then, I've been in places like Motorola, and last 5 years in Red Hat.
Okay, so let's get started. This is the agenda, which I'm not going to read through. I'm just making a point that we've been kind of developing not just this presentation, but what we do on timing and sync in radio access network in presenting in many places, which is on the bottom of this screen. Some international conferences, and plan to continue to do that, which is one of those is today, talking about these topics. So I'll start with not reading through the abbreviations, but it's a good reference taking a look at the end. So we will deliver this deck to everybody once we are done with this presentation today. Now, starting on the key vertical markets with synchronization interests, which is pretty much all enterprises, finance, industry and utilities, broadcast, cable, with a little bit different accuracy targets, which are on the slide, and primary protocols which are used in these vertical markets. Now, going towards the right-hand side of the slide, which is telco, which is of course what we are talking about today, and radio access networks specifically. The accuracy targets or requirements are most stringent in telco, and that's where we are shooting for at Red Hat, which we will of course talk about a lot today. And once we are good with this, then we believe that we are good with other vertical markets as well. Now, just a couple of slides on why timing and sync is needed in radio access network. So fundamentally, accurate timing and synchronization has long been required for telco network or telecommunication network in general. And in radio access network specifically, which is designed to optimize the performance, reliability, and all these things, timing and sync is vital enabler to do that. And it's mostly important on time division duplex model, where radio frames are transmitted and received over the radio between the user equipment and radio base station on the frequency divided into small time slots, which I will talk about on the next slide. So in that space, timing and sync is very important. It's important in frequency division duplex as well, but not that stringent requirements. Now, the radio access networks have been architecturally transformed or changed quite a bit during last few years, specifically when going to 5G new radio model. The radio base station has been divided into 3 different entities, which are called centralized unit, distributed unit, and radio unit, CU, DU, and RU. And this aggregation is by 3GPP standard. And 3GPP, as we all know, is a standardization authority on mobile networks. So that division has to happen by all RAN vendors, no escape from that. And the baseband functionality, which is typically in the vertically integrated into base station in 2G, 3G, and 4G, the baseband functionality is now split between DU and CU. And it's very important to know and understand, which we really don't talk too much about today, is that with this entity division, DU and CU functionality and the entities, logical entities, can be relocated away from the cell site to the edge data center. The radio unit obviously stays on the cell site. There is no way out. That's understandable, next to the antennas. But DU and CU can be relocated away. They still can be on the cell site, no doubt. And some people do that. But they can be relocated away from the cell site to the edge data center, which kind of introduces more challenges for timing and sync, because there will be bigger physical distances between all these entities. Now, a little bit on TDD, time division duplex, which I mentioned earlier. I don't talk about the frequency division duplex today, but time division duplex. So what I was saying is that TDD cells, they can be operating on same frequency or adjacent frequency between the cell sites, and there are overlapping coverage between these areas. So accurate timing is crucial, so to prevent base station or user equipment and user equipment radio frequency interference. That's important, one important factor. And the other important factor is the fact, which is kind of shown on the figure on the right hand side, is that the same frequency is used for both direction, like downlink and uplink direction, and there is a guard period between those very, very small time slot carrying the traffic, the data. So the direction of the traffic is kind of changing on the fly, and timing is crucial to make sure that the user equipment, the mobile device, and the base station are kind of obeying the same timing very, very accurately to be able to capture these time slots. This is a complex topic. And the note at the bottom of the slide is very, very important, or two notes actually. So the note number one is that in cloud, which means O-RAN Alliance, per O-RAN Alliance architecture, the synchronization part or the synchronization chain is part of the cloud infrastructure, and it's decoupled from the RAN workloads. So traditionally, the RAN workloads by RAN vendors, they were taking care of the timing and sync, but now it's decoupled from RAN workloads, and the common cloud infrastructure needs to take care of timing and synchronization chain in disaggregated RAN. And that is the reason, that is one of the reasons why Red Hat is doing what we are doing and what we will be presenting today, because it is a responsibility of what we do in our cloud platform. And the note number two is also important to understand. So in RAN domain related to cloud platforms, we always talk about the real-time execution environment for RAN instances is important, which it is. Hardware accelerators for RAN workloads, specifically on the distributed unit, is highly important, which it is. But synchronization is equally important, maybe even more important than real-time and accelerator. So we kind of rank these three things as most challenging and most important features on disaggregated RAN: real-time, timing and sync, and acceleration. Yeah, and now this is a kind of a great slide, in my opinion. It's a Pasi's work again, which is a RAN synchronization challenge on one slide. So this is a map of US, as everybody can see, and it's a plot of Verizon network out of public data, so nothing to hide here. And this map has, so it's a Verizon cell network, mobile network with more than 500,000 cell sectors on this map, and hundreds of thousands of distributed network elements constituting the whole countrywide mobile network. And these network elements, they need to be synchronized down to 1.5 microsecond absolute timing error to make this thing work, complex thing work, and to make the performance and reliability on the level which is expected. So this is a big challenge. Very quickly, a kind of an edge classification, which diagram we use at Red Hat quite a bit. And there are a few arrows here. The yellow arrow at the bottom of the slide, that is the domain where Kubernetes cluster, Kubernetes container cluster plays a role. And the blue arrow on top of it is connectivity throughout everything. That's all, that's obvious. And what we are talking about today is the green area, which is cell sites, edge cloud, and regional clouds. And with those one-way delay, transport delay numbers, which we are having on top between radio unit and distributed unit, less than 100 microseconds, and radio unit and centralized unit less than 1 millisecond. TPT can be a bit more, but those are the kind of limits under which we need to operate to make the timing and sync work. Just one slide on Red Hat product, just a little bit. It's a Kubernetes-based container platform, which we have been building and are building, and it plays a big role in timing and sync in RAN space as well. And if we start from the bottom, so this container platform can be onboarded or can be running on physical footprint, virtual footprint, and private cloud footprint, public cloud as well. But from the timing and sync point of view, we are focusing on physical, virtual, and private, not public at this point. The next layer, node level mechanism, which is a Linux with real-time capabilities, which is a container host operating system. That layer contains the low-level synchronization mechanisms like protocols and resiliency and hardware enablements and all that stuff, which is kind of obvious. Then the Kubernetes cluster services, the next layer, that manages the one Kubernetes cluster, which can be localized or even remote nodes if that's a desired model. And that level needs to be able to do the configuration and management of the timing chain as well, in addition to other management tasks it does. And the upper layer is, we call it multi-cluster management, which is a functionality which manages geographically distributed clusters, multiple clusters distributed geographically over the region or country or whatever you might have. And even on that level, we need to have configuration capabilities for timing and synchronization chain on the local deployments. A bit of standardization. So our industry is talking a lot about PTP, Precision Time Protocol, which Pasi will talk quite a bit more. So we need to do PTP. There's no doubt, but it has to be understood that PTP is, of course, necessary, but it's not sufficient. Timing and synchronization chain is way much more than Precision Time Protocol, as you can see in subsequent slides. Now, these are the main industry organizations, de facto organization and standardization bodies, which are dealing with timing and sync. And starting on the left-hand side, I mentioned 3GPP already, which is a standardization authority on mobile networks, has been since 3G, 4G and 5G, and now 6G. 2G was originally specified by ETSI, but 3GPP took over in 3G days. And from that, many organizations, de facto organizations like CPRI, Common Public Radio Interface, by NEPs, equipment providers mainly, they took what 3GPP did and specified the protocol between the radio and baseband, which is not really, well, it's not open and it's not multi-vendor capable. But then it has evolved, or it's evolving into enhanced CPRI transport, which is supposed to be multi-vendor capable, and it is, and it will be. Then we obviously have IEEE doing PTP and sync work. We have ITU-D, which has a lot of documents, a lot of profiles, a lot of standards, actually quite or very high quality work on ITU-D and worth reading. There's a lot to read, but definitely worth reading. And all these things, they feed into ORAN Alliance, which is the newest organization working on RAN. So it's an open RAN alliance, and they do a lot of work. And one of the work they do is specifying the architectures. They specify cloudification and orchestration, and they do also specify synchronization in clouds, as shown in this diagram. So I'm gonna stop here and hand over to Pasi for the most of the rest of the slides. Pasi.
All right, thank you, Timo. Okay, to the next one. So from the telco in general and radio access networks perspective, in particular, the couple of the ITU profiles that act as our Bibles, so to speak, the 75.1 full timing support, and to much lesser extent the partial timing support. There's main differences are the transport. The .1 is on the layer 2 Ethernet multicast, and the .2 is using the IPv4 or IPv6 as a transport, and the .2 may also make use of the quality of service mechanisms such as diffserv or the layer 2 QoS with the VLAN tags or combination thereof. And I understand that you are defining your own profile, but so I'm trying to not convert you to RAN people, but point out some of the commonalities and differences. After all, these are just profiles, so as compared to what you guys are doing, as far as I remember from what I have read, you are using the IP as transport, and you are using the transparent clocks on the path, and transparent clocks are actually allowed even on the full timing support, but on the telco cases, the .1 profile is usually used as everything in the path boundary clocks, and oftentimes also combined with the sync-E support. So that's the most common configuration that we see in the telco space, but there are also cases in limited configurations and with maybe lesser performance requirements where the partial timing support is used. So we are definitely supporting both of these and combinations thereof in some cases. So I'm not gonna read it through. You can go through these slides afterwards. So flip the next one. I don't know if I should bother you with this either, but very quickly in the ORAN, there's 4 major synchronization network configurations. The major differences between these are like what you would expect the differences to be in the distributed system configuration. If you think about the operator map that Timo showed, we have like 3 or 4 tiers of different kind of data centers or sites in the network, and you have lots of options on how to implement your synchronization architecture, and they are pretty much every operator's case is different. It depends on what you have in terms of the transport network, existing equipment, the fiber availability, and so on, and whether you are going after DRAM configuration or CRAM configuration. CRAM in this context meaning that at least the DUs are in the centralized pooled site, and the key synchronization point is on the air interface on the radio, and but most other entities and all the entities in the path also need to either be synchronized or pass through the synchronization signals. So the major things here are the location of the reference sources, like a grandmasters, whether you have a hierarchy of them, how do you use them, maybe together or separate if they are in standalone configuration, like extreme configuration. One extreme configuration would be that every cell site has its own GNSS receiver, a grandmaster that has been quite common, especially on the LTE deployments. And the other extreme is that you push the grandmasters as high as you can on the network that meets the accuracy targets associated with the air interface. And then there's combinations of those and everything in between. And the second key aspect, like on any synchronization chain, is how many elements and what kind of elements do you have on that transfer chain. And so I'll leave it there.
Thank you, Pasi. Will you go into the domains where Red Hat is active and describe your work there?
If you are interested, let's go through a little bit on what we're doing here. You can ask questions. Okay. I try to get through this quickly and make some time.
I think we are. Our team is more or less familiar with the standards, and we can go to the other slides.
Yeah. So flip to the next one. So the one thing, this is still of the ORAN's configurations, but in reality, what we need to do and what we do is to break it down to specific synchronization functions and elements, and think about it as a feature set rather than in the context of the ORAN configurations. And there's a couple of reasons for that. One reason is that there's infinite amount of, or nearly infinite amount of specific subsets on those ORAN configurations. And the second reason is that if you go through the implementation of the ITU specs, that what we are fundamentally doing, or any kind of implementation, then you need to really think about these function by function and feature by feature, and that's how the ITU specs are written, and that's kind of how we deal with them. So next one. This is again radio access network specific, but this is a first configuration that the ORAN working group 6, which is the cloudification working group, went after. And basically the idea here is that you have the primary reference source and the grandmaster somewhere in the front haul network between the radio units, which are in this picture on the right, and the DUs, which are on the left, and you synchronize everything from that source. But there's basically the DU synchronization is not as critical in terms of the accuracy requirements as the RU synchronization. And there's additional requirements for the differential timing synchronization between the radios and so on that are not directly applicable to the DUs. And as a consequence of that, the DUs in this architecture only need to behave as slaves, but radios are obviously also slaves. But in some other configurations, like in DRAM cases, we may have to be on the critical transfer path to the radios as well. So next one. So here's kind of slide that I can use to explain what I just said. So it is CRAN configuration. If you think that my definition of the CRAN is that at least the DUs are located in the edge cloud sites, and typically you would like to, if you can, minimize the amount of the grandmasters you have in the system, if you can. And so logical place for the Grandmaster placement on these configurations would be the edge cloud sites, and each edge cloud serves any number of the cell sites, can be up to thousands of cell sectors, so they are not necessarily small. But in this configuration, the DUs are synchronized from the local Grandmaster, and that allows you to relax some of the performance requirements of the intermediate elements for two reasons: because you have less of them, and also because they are not in the critical path for the synchronization towards the DU. So like a fabric element in these edge data centers don't necessarily need sync-E and tightest accuracy classes. But on the other hand, on the path that's facing the radios, especially if you have multiple elements there, they need to support typically sync-E and most commonly stuff like class C timing. And on the DRAM, this is where the boundary clock configurations applicable to us mostly start to come in play. So we have these options on moving the Grandmasters to each side or having them in both sides, and then you typically have a cell site router in many deployments, and that looks like this. But there are also operator cases where they want to eliminate those cell site routers or increase their fan out, and that requires the embedding of the boundary clock functionality in the nodes, which starts to affect us. In that case, we need to support the embedded boundary clock, possibly also embedded Grandmasters and sync-E, and that's all the critical synchronization transfer path. Next one. So I'm not going to go through this very much. I just point out that this is a very simplified picture, like just one NIC and as a slave. We have obviously configurations with the embedded Grandmasters and much more interfaces, redundancy configurations, and configurations with the sync-E, and that affects this software landscape. There's lots of new hardware coming in. We are obviously not hardware company, so we work with all the usual suspects and some unusual suspects on hardware side, but we try to do as much as we can to enable that hardware with the open source software stack. So we use Linux BTP as a basis for the implementation, and then we add those integrations to system level management layers that Timo was talking about in the OpenShift introduction slide. So you have had many presentations on details of this stack, and then you could talk about this. Yes.
I'm sorry. What is the synchronization needed at the user space level, and how do you achieve that? If you can elaborate on that.
Okay, so the synchronization need on the user land is basically we synchronize the system real-time clock, and in the RAN use case, everybody and specifically DU container instances use the time from that clock, at least in most implementations, and that is not extremely. It doesn't need to be extremely accurate. It's basically used primarily in addition to the delay management mechanisms that are embedded in the ORAN front haul specification to control the basically the timing of the transfer towards the information for the RUs from the DU, and but we do want to so basically how it works is that we synchronize the we run the BTP to synchronize the PHC on the NIC, and then we transfer the time from the PHC to the system real-time clock with the PHC to sys process, and all the processes that are running the user are using that as a time. But there's also virtual machine path that's a little bit more complicated, but that's not mostly used in the RAN use cases other than on OpenStack, but that's not the topic of this discussion. But we also support virtual machines in our container platform, so you can have a virtual machine in the container, so that's why that path is here as well. So. Right.
Thank you.
Thank you. So I think that everybody understands this. This is just to point out that how the ITU deals with the synchronization chains is they break it the elements and numbers of elements and allocate the overall misery, the total budget to subsections of the system, and then specify the requirements for each of these components, and that's actually pretty nice decomposition, and you can go and read all of the ITU specs if you are interested. But that really helps us to deal with the combinational explosion, because, like I said, every single operator case is different, and so when you can do the performance testing on element by element basis, and then do network engineering based on what you are trying to accomplish, that's much easier to manage, and that's what key contribution. One of the key contributions, in my opinion, from all the ITU work. Not only one, but that's very well thought out. Next one. So, with respect to the error budgets or accuracy requirements in the context of the ITU profiles that affect us, this is for the .1 profile. The specification for the TTSCs, the slave clocks and boundary clocks, is in G8273.2 spec. There's another one for the puzzle timing support profile, but the requirements up to class C are very much similar. So I didn't make other slides for that. You can read the spec for the details. There are additional requirements for the time error tolerance, but these are the key metrics from the ITU for the slaves and the boundary clocks that we are trying to meet in the notes. Next one. So we've been on this for a while. We started with the generic kind of test gear, the usual reference standards and the scopes and frequency and time interval measurement stuff. We have lots of gear from that, and we kind of concluded that it's lots of work to do the full setup. So we, after we were happy enough that we can meet these requirements with the commercially available hardware, we have invested on the more commercial test equipment that is tailored for the synchronization use cases. The key pieces, the Calnex Paragon Neo PTP conformance and performance test set. We also have Spirent test centers and some EPRTCs and cesium references. We are working on automating everything because we work with lots of hardware vendors, and we can't have infinite amount of this test equipment configurations. And how this works, you kind of have to hook it up to device under test physically. So what I have in order is optical layer 1 switch that allows us to have lots of different NICs and FPGA cards and other kinds of entities, and that allows us to automate the changes for the test configuration, so we can run things like regression testings and so on. That's on order. I don't have it yet, so I still have to drive to the lab to change configurations. Because you guys are doing grandmasters among other things, and so are we. We also have the GNSS simulator in the order, and we have network emulators and lots of different switches and routers and all kinds of stuff that you would expect to see in synchronization lab. So next one. So this is the most simplest possible test configuration that you can come up with for the using the Paragon Neo. This is for the slave testing, and it's very simple. The Neo acts as a master, and your DUT, this configuration, acts as a slave, and you get the feedback signal from the 1 PPS signal, and that is nice if you can do this in many cases on commercial, especially data center targeted NICs. You don't have the 1 PPS signal either wired or available at all, so you might get to it by doing some instrumentation of the cards in such cases, or you might be out of luck because obviously you need some kind of feedback signal to be able to measure where you are. So next one. So this is just one of the very high-level summary on one specific NIC on the ITU as a slave, and these reports are like tens of pages of long even for the slaves, but this is I think this is well within like class C, or kind of getting to class C category requirements for the absolute time error measured from the 1 PPS in one slave implementation. Go to the next one. So because we believe that this synchronization stuff needs to also work in configurations with the traffic, and that is not actually exercised by the ITU standard use case, at least on the 73.2 profiles basics tests. We also test under load, and unfortunately, because the Neo cannot presently act as a load generator, we have to add the switch in between. We still run as a slave, and but we also load the interfaces with basically using like a DPDK test PMD to turn the traffic around. And in some cases, there have been some issues with hardware implementations in this kind of configurations. Go to the next one.
But
Yes.
Pasi, in that setup that like you describe here,
Yeah.
you don't measure the noise coming from the NIC itself. You measure the overall noise.
Well, Yes and no. So you are right in the sense that yes, we have this width in between, and that complicates things. We are getting the feedback signal from the 1BPS interface, but this is the best you can do with the equipment you can buy. And this is better, in my humble opinion, than not doing anything and wondering whether it works. So you are right. It says that this is not ITU standard test configuration. And yes, you have two elements in series, which is not desirable, but that's only way we can currently do this.
We for example connecting the NIC also directly to the Paragon, and by that once we make sure that the NIC comply with the clock requirements, the 8273.2, then we connect the switch and we increase the chain one by one.
Yeah,
but without that solid ground.
Yep, that's also an option, and I think that I have done such configuration as well. It depends on how many ports you have and what you're trying to do. But yes, good point.
Yeah,
Yep.
Michelle, I have one question. I was wondering in your presentation if you're going to go through more of the aspects of cloud native principles and how it applies to synchronization networks. For instance, the applicability of containerized functions or Kubernetes and RUs, DUs, and CUs, again, from the management of a synchronization network.
So I can answer that. I don't have like a lot detailed slides on that, but
Okay.
basically the synchronization functionality, like Timo said, is decoupled from the container instances. That's one problem we have with the ORAN specifications from, say, Working Group 4, that they are written like everything would be still hardware, and even the management interfaces are embedded on the, say, DU or RU management interfaces and YANG models. But when the reason that these are decomposed in the cloud is that, well, there's multiple reasons. One is that's how the customers want them, but also because you can have multiple DU instances in same node, you can't have multiple processes and you stick those timers and so on in the cloud nodes, and those processes are using the system clock directly. There are potential paths to enable the read access to the PHC directly, but so far nobody has asked for those. So implication of all of this is that we as a cloud infrastructure vendor need to take kind of ownership of the synchronization infrastructure. But at the same time, there are things like interfaces, for example, in the DUs, and eventually when we get to the RUs, that if there's a problem with the synchronization state, these instances need notifications, and we are in process of specifying such interface in the ORAN Working Group 6 just for that purpose. And then there's obviously the whole management stack, but that's a complicated topic. I don't think that I have time to go through all of that in this.
It could be a good topic for a future talk.
Yes, it would definitely be something that we could easily talk 1 hour just as a standalone topic. So.
Hi, Pasi. There are a couple of questions that accumulated on the chat, and I wanted to pass them to you. So people are asking about Kubernetes synchronization. In particular, can you run VDU in Kubernetes clusters and still maintain sync at the required level?
There's so first, the answer is yes. So then you have to understand that there's two different things that we are synchronizing. First, we are using the BTP to synchronize the PHC, and that clock gets then transferred to the host real-time clock and used by the containers. The accuracy of that path is sufficient for the DU use cases, and that is not nearly as demanding as keeping the RUs in sync. So some instances, and when you are boundary clock, then that the accuracy of that hardware clock also matters, and it's the same case in the radio. So you have different accuracy levels even on the same system based on whether, the use case, whether it's software process or hardware using those clocks. There's at least two clocks involved. In some cases, you can have multiple cards, so it gets very complicated. But answer is yes, and including that we are getting to the boundary clock cases. So I don't see. And thanks for all our hardware partners. This is not just software problem. This is problem between hardware and software. So
more of a follow-up question. Let's say you have multiple containers in one machine. Obviously,
yes.
You have like, let's say, one NIC. I think appropriately, you don't run, let's say, PTP4L in the container. You rather run it like, let's say, outside the container, so you serve everyone else with a PHC.
Yes.
Or like, let's say, the system clock. But now the question is like, what will happen if I run it basically in the container? Is that even possible? And what will basically, the second question is like, do we have like any method and system where if I have multiple, like, let's say, PTP4L instances running in multiple containers, and how would the system basically, our Red Hat basically, take care of all of this collision or too many cooks? You know?
Yeah. So that's what I quoted before as one reason why you can't have you can have multiple masters taking ownership and adjusting the clock, any single clock. So that would be a mess. That's one reason we have that. You can have multiple instances in parallel associated with different interfaces and possibly even with the different profiles at the same time. And we, if needed, we would manage such configurations. We are trying to avoid those as much as possible, and at least in the single NIC configuration, you don't really need to do that. The complication is that comes from running multiple instances is also that when you have redundancy configurations and masters and slaves, you have to manage like what's active and so on, and it gets even more complicated with the sync ISO. So
yeah, this is more like what I'm trying to do is like I'm trying to like basically systems like multi-host NICs, right? Where you have like, let's say, multiple servers running on the same hardware often, and you can't just have, let's say, one of them acting like, let's say, I mean, there are different methods like we're taking care of it. I'm wondering, do we have also something like at this? I mean, that problem, as I said, like that problem in hardware is solved. Like Dotan can walk you through like all kinds of like tricks and methods. I'm wondering in containers, do you have a way to do that? Like, let's say again, I'm not talking about multiple grandmasters. I'm talking about the ordinary clock. Like, let's say you have again multiple cooks. What will happen? Would it get too salty or?
Yes, you don't, like I said, we say, do not try to have multiple entities adjusting the same clock. So that's the basic rule.
Okay, so it means like there's no mechanism for it to prevent like damage or like, I mean,
no,
misoperation.
That's
Okay.
a really bad idea. So, So let's flip. We already kind of running out of time, so let's flip through a few of these. So this is one example where the TSC performance varies with the load on the right-hand side. Bad thing, don't do that if you're a hardware vendor. Next one. This is boundary clock test configuration. This is actually also useful for dealing with the testing the slaves, because the slave is boundary clock is kind of, you can think about it implicitly as a combination of the master and slave. And so when you have NIC that doesn't have the PPS signal, the just running as a boundary clock is a way to get around that. But next one. Here's some test results on one that is very nice, like a class C. This is even without sync E, so that's nice. Next one. This is so we have lots of grandmasters. This is I put this together today because I know that you are dealing with the grandmasters. That those are definitely of interest for us. So we don't have all of this stuff on hand right now. The GNS simulator is on order. I hope to get it sometime very soon. So because we already have like NICs from multiple sources with the embedded grandmasters. We are also updating the lab configuration on SyncLab to a couple of the PRTCs. We would run at least one of them as a reference source to basically GNS simulator and all the other equipment. And the poor man's version that you can try at home is like taking a couple of the grandmasters and hooking them to one antenna on this guy, from this guy, and same software version running them on the position fixed mode, and just hooking a scope or something on the PPS outputs, and seeing the miracles that happen when you are running same software from same vendor, and then imagining what happens when you are running different vendors and so on. So it was surprising to me what I have seen in such simple configurations, sharing the antenna and length match cables and everything, and you still see quite unexpectedly large deviations between the two instances, which was surprise to me. Go to the next one. All right, what else? This is just a slide on what we are working on. So the basically on our to-do list, the adding the sync E support is a very important priority because of the telco stuff, and I also mentioned the grandmaster integrations already, and generally just keeping up with the hardware. Improvement of the management and monitoring capabilities, especially in the large system configurations and populations, like automatic resolution of what's actually faulty in the whole synchronization network when it's distributed and that kind of stuff. And like I said already, we could talk about that alone for hour. And performance improvements, especially on the path from the the hardware clock on the NIC to the system clock. That's the kind of like a weakest link in the chain from what we see so far. Go to the next one. This. I was hoping that we would have time to talk about a little bit of these things. I have while I haven't had time to attend all of your meetings, I have been I'm on your mailing list, and we have been consistently referring to you guys so that you are working on the synchronization stuff as well on our talks, and I'm definitely reading your material and going through your presentations as well. So I'm aware of what you're doing, and based on that, I kind of thought that these might be some areas that we have some common interest at the very least. After all, it's the underlying things are same irrespective of the profile for most purposes, and things like testing and as far as I know, we all use Linux BTP, and so there's a lot of common, and we are obviously interested in grandmasters as well, but we need SyncE on telco market for on those as well. So I'll stop there.
Pasi, I think that this is where, if you can go one slide up, this is where we want to take the follow-up sections and the follow-up matters, and we have the working group for APIs, which has been which is definitely a good place to host such follow-up discussions. I know the team was expecting a little bit more on that, but we ran out of time.
Although we're like on top of the hour, let's give it like another 3 minutes, like 5 minutes basic total, because I think like it would be a pity if we don't, like, I don't know, give enough opportunity or not enough love to this slide. So
I have a question for you guys. The one with the question mark. You have the work stream on the clock performance and accuracy APIs, as far as I know, but I don't know if there's what's the state of that and how you go about working on that, because that's definitely something that it would benefit everybody if we can get something on the Linux. I don't think that the API is a problem. How do you get the information to feed that API is interesting part.
So we have like coming up some news soon, and basically like my colleagues like they're working on some new APIs. Like it comes in a package. The difference between, let's say, those APIs and let's say other things that you see, like how fast we're like publishing things, is there is an entire process of like open sourcing pieces of software and so on. That's why it's taking a little bit long. But overall, like I make just like a, what do you call, a sneak peek. You can imagine like all the development that we did with like on the open source Grandmaster with a time card and so on. There is equally the same effort on the software side of it. Like, for example, what I want to ask you guys is, like, do you guys use anything other than PTP4L for the Grandmaster when you want to turn like basically one of the nodes as a Grandmaster, or not? Like, or you have your own thing? Like, I mean, from Red Hat's package, I see it's like pretty much like PTP4L. You put it like as a Grandmaster mode, master mode. Like, is there anything else like you guys have for it, or?
So we try to not have anything else. We try to, obviously we are Red Hat, so there's no such thing as there's some closed secret source that is not in open source or won't be in open source. So everything we do will be
more than secret. Out there. Is there any vision for making something? This is more like.
On the Grandmaster specifically, not yet, because I don't know what problems to expect, because we are just getting the hardware on our hands to start testing with those. But maybe we do have
a time card. Yeah, I can send you a time card, and then you guys. I mean, the driver is all part of Linux kernel 5.6 plus. Like, if you've seen, I'm pretty sure you've seen the GitHub repository for it, like timingcard.com.
Yeah.
So timingcard.com, you go there, you see everything about it. So the scale was one issue there, like a lot of different things, like PTP4L as a grandmaster, not necessarily the best solution. It has problems with the timeout of like unicast, a lot of problems. So the utilization, there is a cap of 1024. Did you know that? Like, like you reach 1024 clients, it crashes. There are a lot of problems with it. So
yes,
that's
so
what those.
yeah, I understand that. That's your use case is also quite different because you want to have like end-to-end transparent clocks and one very highly scalable grandmaster. I think that there are probably ways to do a lot so to improve that. Maybe even going all the way to something like DPDK kind of implementation instead. But we don't expect to see that problem in these cases because it's a kind of chain, and we don't unless we do the exact same configuration. But there's definitely something that we could take a look and discuss with you guys.
I don't know. Is anyone else has a question?
Yeah, I have a question. So what Red Hat provide open source code? So what code you provide here? You provide what kind of code you provide?
Well, we don't. So we don't provide code. We provide product that is based on the open source code, and so that's what we sell. And we sell support and services and integration and maintaining that stuff. But everything that we do is based on open source, and we work on the I don't know, hundreds of, if not thousands of upstream projects, including the Linux BTP and many others. So,
I think like perhaps like what I can add to what Hisham is asking is like, is there a specific add-on when you go and let's say run PTP4L, let's say in Red Hat, or because I saw like that KVM module you have. Like, is that something specific to you? What you guys have, or?
No, it's
not okay.
So while everything is open source, it might be distributed to different projects. I think that because like that aspect to getting the VMs, that's involves the KVM and so on. So at least some pieces are there. So you kind of have to know how this is put together, and which is not obvious to most people. So
one last question that actually I really looked forward to basically ask today was, we did a test. We basically built a test setup where we had basically on a machine multiple NICs, and then we isolated the NICs. Like we were trying to basically simulate a chain of let's say 5 boundary clocks with a grandmaster and ordinary clock to just basically play on the servo and see how the servo is reacting and so on, between parameters of the servo and do tuning and so on. So what we did is like we basically put 5 NICs on one machine, and we isolated every NIC with a network namespace. And then in every network namespace, depending on where it was sitting, we basically had like 1 or 2 instances of PTP4L, one acting as a master, one acting as an ordinary. And we basically made a nice like chain of like boundary clocks. So now I'm wondering, can I do the same thing with your containers? Can the containers take a hardware NIC without compromising any, let's say, the timestamping and so on, and then basically build the same thing in a cleaner way? Because like I mean, network namespace is not the best thing to do.
Yes, I would think so. As long as basically containers are just they contain processes, and yes, we can contain the BTP processes, and that's how we deal with everything anyway, unless we run as a service. So yes, that's not possible as long as you associate those with the different hardware clocks. I don't see any problem of actually doing that.
So like a short answer is like like basic containers can do the job of this network namespace, right? The isolation, right?
Yes.
Yeah. Great. Okay, I think we're really now on top of the hour by 10 minutes, so I think we can probably adjourn.
Yeah, thank you very much, Pasi.
Thank you, Pasi.
Thank you very much.
For the
And
presentation
I will
and all the wonderful questions.
Thank you, Timo, as well.
Thank you.
Thank you, everyone.
Thank you.
Thank you, Timo.
Thank you.
Thanks. Bye.
Okay, bye, everyone.